Hello, so today we are going to learn how to solve a game as an LPP. If you remember, we had done something about how to solve a 2x2 game and also how to solve a game with only two rows or having only two columns by graphical method. We had also learned how to solve a game by using the dominance property. That is exactly for reducing the size of a game. But this method that we are going to learn, it will be applicable for all the types of games that we will be having. Okay, so let us just go ahead with it. We will try to convert the problem of a game into an LPP. So let there be a zero-sum game between A and B with P of matrix as in the board. Okay, so let SA be the optimum strategies where these are the restriction. The restriction of probabilities is that the sum should be equal to 1. Similarly, the probabilities for B, should be equal to 1, the sum of the probabilities. So if we have to solve it, you will have to solve it separately for player A, for player B, even though later on we will see that how solving for one player ultimately leads to a solution for the other player as well. Because ultimately player A and player B, they are both connected by this P of matrix. So let us see. Okay, so let us try to formulate an LPP for player A. Okay, so let's see. For player A, remember that player A wants to maximize his profit. So what will he do? He will first take a look at B's strategy and he will calculate his payoff. When B strategy, okay, so the possible strategies for B is B1 up to Bn. So that's why over here we are having B1, B2 up to Bn. And what is A's payoff? A's payoff, if it is B1, it will be A11, A11, P1 plus A21, P2 plus AM1, AM1, PM. Okay, so these are the payoff for player A when the strategy is B1. Similarly, when the strategy is B2, you will have to take this column, which is A12, P1 plus A22, P2 plus so on up to AM2, PM. Similarly, we can go like this for the last strategy, that is Bn. The payoff will be A1n P1 plus A2n P2 up to AMN PM. This is AMN. Okay, so after doing this, so what will be the problem for player A? Hence, the problem for player A is, for player A, remember that A is trying to maximize his profit. So first of all, he will calculate all of these payoff. He will try to look at the least payoff that he can get. Okay, so first of all, he will take a look at the least payoff, which is how many entries you are having over here, B1 up to Bn. Remember, okay, we are following some sort of a rule over here that J runs from 1 to up to n. J equal 1, J equal 2, J equal n. Whereas if you are using I will be 1, 2 up to m. Okay, so remember that. So over here we are having B1 up to Bn. So how many of entries will be inside this bracket? We will be having n entries. Okay, so will be 1 less than J less than n, because we are having n entries. The minimum of these n entries, okay, which can be written, each of these one, it can be written as a summation. Okay, for example, if it is Bj, then it will be A1j P1 plus A2j P2 plus it will be A1j P1 plus A2j P2 plus AMJ PM. Okay, so that is what we are doing over here. So over here will be Aij. Again, over here the summation is from 1 up to m. So Pi, I equal 1 up to m. Okay, I equal 1 up to m, because probabilities from 1 to m, similarly 1 to up to m. Okay, so it works. Yeah, JPI. So the problem for player A, he has first find out his least P of that he is guaranteed. What will he try to do next? He will try to maximize it. How can he maximize it? He can maximize it by adjusting the probabilities. Okay, he has control over these probabilities. He can change his strategy anytime. He may not be able to change player B's strategy, but he can surely change his own strategy. That is by changing these probabilities Pi. Okay, subject to P1, P2 up to Pm equal 1. Okay, so now it is starting to look like an LPP. We are having a maximization problem of this thing, subject to this, but it is still not yet an LPP. It is not yet an LPP because even though we are having the constraint, it is linear, whereas over here, this part over here is not linear because we are still having minimization in between. If there is no minimization problem over here, then maximize just of this one, it will be an LPP because this one is linear. But because of this minimization problem, it is not yet linear. So that's why first of all we will have to do something about it. Okay, so what can we do? To convert it into an LPP, what can we do? We can let this whole thing to be equal to u. Okay, so let u equal to minimum. This minimum 1 less than j less than n, I equal 1 up to m, aijpi. We are substituting this one so that ultimately we will get only maximization of u. Okay, so once you replace it, you will get maximization of u. So we will start it to become like an LPP. We are having only one variable, which is u. Okay, but you will see that the final thing will be related to just what I had said. Okay, so keep in mind this matrix. Okay, since u is the minimum, so what can we say? If it is the minimum of all these values, so these values will be less than u. It will be greater than u. Okay, so what can we say? We can say that aij pi, I equal 1 up to m, it will be greater or equal to u. For all j equal 1 up to m. For all j equal 1 to m. Okay, so over here, how many inequalities are we having? We are having n inequalities. Okay, even though it looks like one inequality, because of this restriction, but because of this condition, actually we are having n inequalities. Okay, so what can we do next? Okay, I will just write the steps. We can divide whole thing by u. Over here, u, it is the minimum payoff for player A. We can divide it by u, there's no harm. Okay, but let's see, we can divide it by the minimum payoff. But we don't want the sign of the inequality to change. So for that, u has to be positive. But can we guarantee that this minimum payoff will be positive for all j equal 1 to n if u is greater than 0. Okay, if u is greater than 0, of course we can divide it and the inequalities will not change. But you must remember this one. The minimum payoff, it depends upon the matrix, the payoff matrix. So if there are some negative entries, for example, okay, maybe -1, 2, -3, 4. So the minimum payoff for player A, it can easily be a negative number. How do we avoid a negative number? Because over here we want to divide by something which is positive. How can we avoid that? We can avoid that by adding to each of these values, a fixed number. Okay, for example, we can add the number 4. Adding 4 If all of them are already positive, then of course the minimum payoff will also be positive. But if some of them are negative, we can easily add the number 4 or some other number, okay, maybe 5 or 6. Okay, adding 4, we will be getting 3, 6, 1, 8. Okay, so after adding, we will be getting this matrix. And the minimum payoff for this new matrix, of course, it will be positive because all the entries are positive. But can we do it? Of course, we can do it. Just think of it in this way. If this is a game between player A and player B, okay, you can see that A, sometimes he is having negative payoff. But if he wants to have positive payoff, what he can do is, before the start of the game, he can just ask for some amount. Okay, just give me 4. Okay, at the very beginning. Okay, so that is why we can do it. Okay, but afterwards, okay, it will not affect the game because it will not affect the game because the game only depends on the strategy. Of course, it will change the payoff, but ultimately the probabilities will not change. Okay, what he can do, because the payoff has changed after playing the game, he can return this 4 back. Okay, he can return it, that is by subtracting. So first you are adding it, after solving it, after playing the game, he can return 4. He can return the amount that was given to him. Okay, so you can do it. Okay, so that is why if u is greater than 0, we can do it. Okay, but actually u, it can always be greater than 0 just by adding some constant. Okay, this one we can write it like this. Here I equal 1 to m. Aij pi by u, we can write it as xi greater than 1. Okay, u greater than 0 if for all j equal 1 to n. And over here we have introduced this xi. It is very clear what is xi. Xi is pi by u, where xi equal pi by u. Okay, so the LPP, so the problem for player A becomes summation maximize P maximize U because we have to replace everything by U, subject to summation I equal 1 to m aij xi greater or equal to 1 for all j equal 1 to n. And we are still having a restriction on the probabilities, p1 plus p2 up to pm is equal to 1. Also note something over here, that the probabilities, it is positive or it can be greater than 0. So xi will be greater or equal to 0. U is also positive. Pi is non-negative. U is positive. So xi will always be greater or equal to 0. Okay, so keep a note of that. Okay, so now this one, it is looking like an LPP, but there is still one thing left that we have to do. If you remember that Z, okay, when we write an LPP, we usually write as max Z equal something over here where the variables are involved. Over here, the variables are now x1, x2 up to xn up to xm, but over here we have not written anything for u. Okay, so it is starting to take shape, but we can do one more step. We can write this last step, the required LPP for player A is now what we can do, maximize, we can convert it into a minimization problem. Okay, why exactly we are doing it? Instead of u, we will be getting 1 by u. Okay, this is very simple to understand. If you are maximizing u, it means that 1 by u is minimized. If u is very, very large, 1 by u is very, very small. Okay, this one, if you notice, we can write it as x1 plus x2 up to xm. Subject to, okay, I will explain this line, subject to, but I will write it up. These constraints. Yeah, ij, xi greater or equal to 1 for j equal 1 to n. Okay, this one I will not write it anymore, but I will just write xi greater or equal to 0. How exactly did I get this line, and why did I omit this part here? Okay, it is actually because of this reason. Okay, let's see. x1 plus x2 up to xm. If you write it down, if you remember, we have replaced x1 by p1 by u plus p2 by u plus pm by u. So you will be getting this. So this one over here is equal to 1 upon u. Okay, so we are getting this line because of by using this. Okay, so that's why we no longer need this one in the constraint, because we have already used it over here. Okay, so I hope that is clear. So this is the required LPP for player A. Okay, now it is looking like an LPP. Instead of Z, we are having 1 by U. But to solve this one, remember that one of the techniques that we have for solving an LPP is the simplex method. The simplex method requires that you should convert this one into a maximization problem. But this one is a minimization problem. Of course, we can easily do it, okay, just by using minus the negative sign. Okay, but we don't want to do that. How will we avoid the negative sign here? Okay, we can easily do it by solving the game for player B. Okay, so this is the required LPP for player A. What we can do the same steps, but we will do it for player B. Okay, again I will explain. Let's see. Okay, so this is the required LPP for player A. Now let us see what is the required LPP for player B. For player B, if you are solving the game for player B, then B will think of this in this way: A is strategy, B is payoff. So A has how many strategies? Has A1, A2 up to AM strategies, and B's payoff, it will be the row. Now the row will be A11 Q1 plus A12 Q2 plus A1N Q1. Okay, similarly over here we are having A21 Q1 plus A22 Q2 plus A2N Qn. Similarly AM1 Q1, AM2 Q2 up to AMN Qn. So these are the possible payoffs for B when A strategies are A1 up to AM. B, remember that he wants to minimize his loss. So what will he do? He will calculate the maximum out of all of this. That is the maximum loss that he can suffer. Then he will try to maximize that minimum loss. Therefore, the problem for B is he will try to minimize his maximum loss. These are the losses that he can incur. So all of these losses can be written as summation Aij. Again, we Q1, Q2 up to Qn. So Qj, j equal 1 to n. And how many entries are over here? A1 up to am. So 1 less than I less than m. Okay, so this one is the maximum loss. He will try to minimize it. He can minimize it by changing the probabilities. That's why I'm writing over here Q. Okay, so I hope that is clear. Okay, subject to, again we are having the same thing. The only restriction is that the sum of the probabilities should be equal to 1. Okay, again, this one is not an LPP. To convert it into an LPP, again, we are writing the same thing. We will replace this whole thing by W. Okay, you can use another letter. It's no harm. Okay, replace it by another letter. Maximize 1 less than I less than M summation Aij Qj j equal 1 up to N. Okay, so since W it is the maximum, so all of these entries, therefore all of these entries summation j equal 1 up to N Aij Qj, they will all be smaller or equal to W. For all of these, for all I equal 1 to M. Again, now what we can do, we can divide the whole thing by W, okay, which is positive. We can really do that just by adding some positive constant at the very beginning. J equal 1 to N. Aij Qj by W less than or equal to 1 to M. Again, over here, if W is greater than 0. So we can't really do it. Next, it is the same thing. We can replace this one by another variable. Instead of Qj by W, we can write it as another variable Yi. We have already used Xi, so over here we can use Yj for all I equal 1 to M, where Yj equal Qj by W. Okay, so this is how we do it. Okay, so hence the problem becomes again the same thing. Minimize W subject to, now you are having these constraints, this one as a constraint subject to summation Aij Yj less than 1 for all I equal 1 to M, and we are still having the restriction on the probabilities as well, and Q1 plus Q2 up to Qn, it should be equal to 1. Okay, so but again we can actually write this one into an LPP. Okay, instead of minimize W, we can write maximize 1 by W. The required LPP for player B is maximize 1 by W equal Y1 plus Y2 up to Yn, subject to these things, Aij Yj less than 1, j equal 1 to N for all I equal 1 to M. And also we are having the negative condition, non-negative conditions, which is Y1, Y2 to Yn will be greater or equal to 0. Again, how did we get from this line to this line, and where did this one disappear to? You can actually see this one, Y1 plus Y2 up to Yn. If you add all of them, Y1 it will be Q1 upon W plus Q2 upon W plus Qn upon W. So this one ultimately we will be getting 1 by W, because Q1 plus Q2 up to Qn is equal to 1. So this is the required LPP for player B. Okay, so again, if you remember from the very beginning, if I say that if you have to solve a game, you will have to solve the LPP both for player A and for player B. But actually we can do something else. We can only solve for one player. and the solution for the other player will be given from the simplex table only. So over here, what we will do is, whenever we have to solve a game as an LPP, we will solve it for player B. Okay, then after getting the solution for player B, we can easily get the solution for player A as well, because the LPP for player A and the LPP for player B, okay, it is like a primal and a dual LPP. Okay, so they are dual to each other. Okay, I can say something like that. Okay, so remember that we will solve the game for player B because it is already a maximization problem. We will solve it by a simplex method. The solution for player A we can easily obtain from the simplex table after solving for player B. Okay, we will do some numericals highlighting that in the next video. Until then, okay, take care.